In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 2, Stress Analysis. Part 1. Now, in this chapter, we are going to talk about stress, its origin, and how we define it, and basically about these points. The precise definition of stress. What are internal stresses? What is the stress at a point? What is the principal stress? How do we define the components of a stress? Stresses on an arbitrary plane. What is the transformation of stress? How to find the principal stresses? What is the stress invariant? What is the stress deviatoric? What is the pi plane? And what are their significance? Okay, first of all, I would like to remind you about the materials that you learned in the strengths of materials, and this is just a review and a reminder to everybody what we are talking about, the stress. Well, in this figure, as you can see, we have this ski lift. It has a wheel which is turning like that. It has a vertical shaft here which is connected to the motor and gearbox, and this is the cable. This is the cable on which those people who want to go up the hill for skiing, they are lifted and they are carried out. Sometimes a cabin is hanged on this cable, and therefore this cable must be a very strong material and must be sufficient to resist the forces applied on it. Okay, so what kind of stress on this cable? Tensile stress is applied on this cable, and that's the part of the cable, that's the cross section, that's the tensile force. Therefore, we have a tensile stress on the cable. Okay, what about other parts? That's the drive shaft, as I said, and so one end of this drive shaft is in the gearbox and motor, and the other part is over here. So torsion or moments are applied to this shaft, and we get shear force on an element on the shaft. Okay, Fs is the shear force, A0 is the cross-sectional area on which the shear force acts. Okay, this is due to the fact that one end is over here which is free, and one end is fixed down there. When the power is applied to this shaft, it tries to turn it, but there is a big load in here, big inertia, and so to drive it, it has to apply the power and the force, and then this shaft is under the action of torsion. Now then, let's see. Also here we can write tau like that. That's the torsion. That's the area. That's the area, and that is the radius. Okay. So another one example is the compression, compressive stresses. We have this big stone on the top of this rock, and if we consider an element in here, this element will be under compressive forces because we have this weight over there and we have this rock sitting here, So this element is between these two and is under compressive forces. And compression or compressive stress is F over A0. Another one. This is another example for compressive forces in a bridge. This is Canyon Bridge, Los Alamos in United States, and we have this structure member which is under compression because the load is on the top of the bridge, and this arc is a structure which holds it from this side to that side, this span, and therefore this is under compression too, like that. We could also have stresses applied to an element of the material at different directions, because so far I talked about uniaxial compressive or tensile stresses. Obviously we have many other situations where we have multi-axial stresses, like here we have biaxial. This is a cylinder pressurized tank. We have a gas inside it which is under pressure, and the cylinder must resist the pressure which is inside. So if we take an element on the surface like that, if we take an element on the surface of the cylinder, then we have hoop stress and we have axial stress, which are both positive, obviously. Because as the gas expands or is under pressure, it expands, and the cylinder wants to expand. Of course, it doesn't expand much, but still the stresses which are going to expand it are positive, like this. Another example is a fish underwater. Obviously, we have here hydrostatic pressure from all over the place on all the points on the fish body, and an element of the fish body like that, you can see that these are all showing that the pressure are applied, and so we have sigma h hydrostatic stress or pressure, which is compressive, so we show it with a minus sign. So that's the stress. But what are we going to talk about in this chapter? The idea of a stress is not difficult to visualize, to conceptualize, as I explained in the previous slides. And you have already studied in your BSc in strength of material and in other courses different kinds of stress, and I'm sure that you know enough about it. But if you since objects interact with each other, in what you have studied so far, you have studied objects applying forces to each other, and therefore you can understand how the stress is evolved. However, a more difficult concept is that the idea of forces as stresses inside the material. We have a body of material which is under external forces. Obviously, there are external stresses, but how the internal forces and internal stresses are formed within the interior, where neither eye nor experiment can reach to see whether there is an stress or not. Okay? As the Euler put it, he said that a more difficult concept is the idea of forces and stresses acting inside the material within the interior, where neither eye nor experiment can reach. That's very interesting. Well, it took many great minds and many years. Many people, scientists, worked for centuries, hundreds of years, to reach an answer for this question. Okay? to really visualize and conceptualize the concept, the precise concept of stress that we know today. And the final result, in fact, was reached by Cauchy, which is a great mathematician and scientist. And he, in 1822, in a paper published in Academy of Science in Paris, presented the idea of the concept of stress. Okay? Cauchy's concept of stress. What is it? What did he say? Well, in order to define the concept of stress, Cauchy visualized a slender bar like that. At both ends, these forces are applied, equal forces are applied. Therefore, this bar is under equilibrium. Then Cauchy says that if the complete block is in equilibrium, then any subdivision of the block must be in equilibrium also. So if we take a division here or there, the plane in here also must be in equilibrium. So he cut it in an imaginary plane like that and reached this figure. So if all of it is in equilibrium, all parts must be in equilibrium. By imagining the block to be cut in half and considering the free body diagram of each half, here we are considering the free body diagram of each half, we could see that a force F must act within the block, inside the block, so that each half also is in equilibrium. If all the block is in equilibrium, each half of it should be in equilibrium. And if we divide this half also in two, all the parts that we divide must be in equilibrium. The external loads create internal forces. Internal forces represent the action of one part of a material on another part of the material. Okay? So we can take it that a uniform stress acts over this interior surface like that. Sigma is equal to F over A. Note that if the internal forces were not acting over the internal surfaces, the two halves of the block would fly apart. One can thus regard the internal forces as those required to maintain material in an uncut state. So it means that if there weren't any internal forces, if we apply one force here and one force there in the previous, in here, like that, then it will be cut off and fly away, Why doesn't it cut off? Because there are internal forces to keep the material intact. Okay? So we understand what the internal forces are. Internal forces are stresses, are due to the external forces applied at the body to keep the body intact. Okay? Obviously, if we increase the external force enough, the material has a strength, and if we reach that strength, the material fails and will break. But before breaking, nothing happens, okay, or elastic deformation happens. Now, if we have an inclined planes like this, if the internal surface is at an inclined plane, then the internal force required for equilibrium will not act normal to the surface, because we have an inclined plane like this. Then we say that the normal force will not act for the equilibrium at the surface, what happens? There will be components of the force, normal and tangential to the surface, and thus both normal and shear stresses must arise. Okay, like that. Of course, I explained this in the introduction because at that time I wanted to show you how shear or slip occurs. But here we are not talking about the slip or shear, we are just talking about the component of stress. Okay, so for equilibrium, to maintain equilibrium, we have to have components of stresses like that, so that the resolved force will be in this direction. Okay, and so even though the material is subjected to a purely normal load, internal shear stresses develop. So that's why then we have shear stresses here, okay? Because we have this stress to maintain the equilibrium, and then this force to maintain the equilibrium, and this force must have a normal like that and shear like that, because there is an angle on this plane and we have components of the force on the angle like that. So we get sigma n and sigma s. I explained this in the introduction. We get it F over A cos squared theta, F over A sine theta, cos theta are the normal and shear components of stresses on this plane. Right. So we see that we could have a plane with different angles. Yeah, we have theta here. If we change theta, sigma n and sigma s change. Obviously F over A is constant. So we could have many planes here. Planes going through there, planes going through there. So if we take one point, internal point, inside the body, we could pass through it many planes with different angles. Then if we want to define the stress at that point, which planes do we take? Yeah, because it's just a point. We want to know what is the stress at that point. But at that point, we have many planes passing through that points with different theta, and we have shown that normal stress and shear stress on different planes have different values. So how do we define the stress at an internal point? Okay. For example, if we consider this point as shown in the figure, the stress, as I explained, depends on which surface through that point we are considering. Okay. So the normal stress at the point is maximum when F over A and is equal to F over A. Normal point, normal stress at that point is this. But depending on which plane we are considering, we want to know what is the minimum and maximum. So sigma n is maximum if theta is 0. Okay? Theta is 0, sigma n is maximum. And is minimum when theta is 90 degree. When theta is 90 degree, cos theta, cos 90 is 0, and then sigma n is equal to 0, and that is the minimum value for sigma n. Okay, so that's how we get the minimum and maximum. Obviously theta changes from 0 to 90, we get different values for sigma n. Therefore this plane is very important. We have one point, what different stresses at this point, acting normal like that. If we change the plane, it's not the same point but different normals. So we have many stresses at one point. Okay, But the maximum normal stress at this point in the material or any point in the material has a special significance. For example, it is this stress value which often determines whether a material fails or not. You may remember that in your BSc course, when we were talking about failure and failure criteria, we had one criteria which was based on normal stress. So when normal stress reaches the maximum, the material fails. So it has this significance. It is important. Okay? So we say here that it has a special name which is called maximum principal stress. So maximum principal stress is the stress normal to the plane. Any plane that we consider inside the material, the stress normal to that is the maximum principal stress. And the maximum shear stress on that plane, which is on that point, is plus minus F over 2A and arises on the surface inclined at theta equal to 45 degrees. Yeah, because if that is 45 and that's 45, this becomes maximum. We have shown this before. So 45, 1 over root 2, 1 over root 2, it multiplied together, we get F over 2A. That is it. And because it can have a positive and negative directions or angles, we get plus minus F over 2A is the maximum shear stress at theta equal to 45 degrees. Obviously, for theta equal to other angles, we get other values for the shear stress. But here we have shown the maximum principal stress and maximum shear stress.